Hello everyone. Today we are going to look at section 9.2, which is on the law of conservation of momentum. So we have looked at momentum, we've looked at impulse, now we're going to take a look at what happens if you have what we call a system of objects and the total momentum of the system. So our learning target today is to mathematically support the law of conservation of momentum. And our questions are, under what conditions is momentum conserved? How does Newton's law relate to the conservation of momentum? And how do we use the law of conservation of momentum to predict the behavior of objects? So we need to do some review first to make sure that we remember what all these things are before we start talking about them. So first review question down here, Newton's third law. Now remember, the first law says an object in motion stays in motion. An object at rest stays at rest unless an outside force acts on it. The second law is our formula, F equals ma. And the third law says that forces come in pairs. The pairs are equal in size and opposite in direction. So remember, we talked about things like if you have a table and you have a book sitting on a table, there's a downward force because of gravity, but there's an upward force because of the table. We call that the normal force. So remember, equal and opposite forces. Okay. Definition of momentum. So this is very recent. Hopefully you remember this one. Momentum is the tendency of a moving object to keep moving. And remember, that's why impulses are important, right? Impulses are going to change that movement. Otherwise, it's just going to keep going. Okay, our impulse momentum theorem, that's what we worked on in class last time. And so the impulse momentum theorem says the impulse on an object is equal to the change in momentum. And we wrote that as I is for impulse, is equal to the change. So remember, that triangle means change in momentum. P stands for momentum. Okay? The impulse on an object is equal to the change in momentum. And last but not least, here's the formula that we're going to be working with today, our momentum formula. So P stands for momentum, is mass times velocity. We want our mass in kilograms. We want our velocity in meters per second. So momentum is kilogram meters per second. All right, so those are the values that we are going to be working with today. So the first thing we're going to address is the conditions under which momentum is conserved. So let's take a look. Now, first of all, this should look pretty familiar. We worked with this little gizmo in class last time. And so the first thing we're going to do is define what's different about this setup than what we had in class last time. So in class, we worked with masses of 3 kilograms, but you can see here we have the mass of 4 kilograms. The velocity is the same. We're still looking at 5 meters per second. The other thing I changed was this little slider right here. When we were working with this in class, I had it all the way up here at 1, but now I've moved it all the way down here, so the elasticity is 0. What that means is that these two things are more solid. They are less likely to bounce, okay? They're more solid. So let me get rid of all this. Okay. So what is a system? So that's one of the things that we need to know because we have to define our system before we can analyze it. So a system, oh, I forgot to use the box, didn't I? It's much neater when I use the box. Where is my box? There it is. A system is 2, it could be more than 2, but we're going to stick with 2 objects that are involved L, oh, gosh, I wish I could spell, involved with the action in the problem. That's kind of vague, isn't it? Well, what that means is in this particular problem, we're going to have these two gliders run into each other, okay? So the action is going to be a collision. So these two things, glider 1 and glider 2, that are part of our system here, and they're part of the system because they're the ones that are going to be moving around. Okay, and so we're going to be more specific. We're going to look at what a closed, isolated system is. So these are two very specific conditions that have to be true in order for this law to work. A closed system is one in which the mass stays constant. What does that mean? That means that in the middle of the problem, the glider is not going to go from 2 kilograms to 3 kilograms or 2 kilograms down to 1 kilogram. Okay, the mass is going to remain constant. And then isolated, an isolated system is one in which there are no outside forces. What does that mean? That means that we're going to ignore friction, right? Friction is considered an outside force that would affect my problem, but I'm going to pretend there isn't any friction. That's why it's on the little air gliders. The wind isn't blowing. There's nothing that the two gliders are going to run into on the track. In the middle of the problem, we're not going to drop a bowling ball on the track, right? No outside forces. It's just these two gliders hitting each other. That's our whole action. Okay, so those are our conditions that we have to meet. So let's get into it. The law of conservation of momentum says then in a closed, isolated system. Okay, let's interpret that. In a closed, isolated system, that means the system is our two gliders. Closed means that their mass is going to stay the same. Isolated means it's just the two gliders we're worried about, not friction, not air resistance, not bowling balls being randomly dropped, nothing, okay? Just these two gliders and their mass will stay constant. So in a closed, isolated system, momentum will remain constant. All right, so that means that the momentum that's present in the system before I make it move is going to be the same momentum, or should be the same momentum that's in the system after these two gliders start moving. Okay, so we're going to do some math here. It says, calculate the momentum of the system before the gliders collide with each other. So since both of these things are part of the system, I have to know the momentum of both pieces of the system in order to find the momentum of the entire system. So when I look up here, I see that both these gliders have a mass of 2 kilograms, and I see that glider 1 has a velocity of 5 and glider 2 has a velocity of 0. In order to find momentum, all I need are mass and velocity, so I am good. So glider 1, P equals mv. My mass was 2, my velocity was 5. I have 10 kilogram meters per second. That's the momentum of glider 1. Glider 2, P equals mv. Mass is 2, velocity was 0. Momentum of glider 2 is 0 kilogram meters per second. So we talked about this in class 2, right? If something is not moving, then that means it doesn't have any momentum. So how do I find the momentum of the system? Well, I am going to say the momentum of the system is the momentum of glider 1 plus the momentum of glider 2. So I've got 10 plus 0, so I have a momentum of 10 kilogram meters per second. And this is the momentum of the system, the sum of the parts, right? The sum of the momentum of glider 1 plus the sum of the, plus the momentum of glider 2. So 10 kilogram meters per second altogether. All right, so now it's your turn. So I want you to think about what's going to happen is I'm going to push play, just like I did in class. Glider 1 is going to move. Glider 2 is just going to sit here. And I want you to think, just like we did in class, of all the things that could possibly happen when glider 1 hits glider 2. All right? So there is your space to put those down. What could happen when glider 1 hits glider 2? I would like you to come up with at least 2 possibilities. All right? So pause the recording. Put your 2 possibilities down there. And then we'll go on. All right, so hopefully you have some guesses down there. What we are going to do, and I can't show it to you, unfortunately, I can't insert the little video, is that we're going to assume that glider 1 moves forward, hits glider 2, so they collide, and then we're going to say that they stick together. Now this is different than what we did in class, right? Because in class we had the 2 and they bounced off each other, and they either bounced forward or they bounced back. But in this particular case, we're going to have them stick together. This technically is called an inelastic collision, right? So this would be what happens if, let's see, if you had Velcro attached to something and you rolled something and it Velcroed to something else and so it's stuck together. Or if you were in a car accident and the one car and the other car, they locked bumpers, okay? So somehow they collided and they stuck together. If you were ice skating and you ran into somebody and grabbed them around the waist, right? So you would kind of like stick together, all right? And so then I want you to notice how they look in the diagram. So remember that glider 1 was over here, glider 2 was right here. This one slid forward, it hit this one, and now they are connected and they are sliding off together. Okay? If you take a look, we can see, right, the mass. There's the mass, 2 kilograms. Here's this mass, 2 kilograms. Here's our velocity. What else? I think that's it. We don't care about the time this time. All right? So over here, it's going to be your turn again. This first one says, compare the before and after pictures. List at least 2 differences. 2 differences. This one says list 2 similarities. So I want you to pause the recording again, list your differences and similarities, and then we will go on. All right, hope you put your similarities and differences on there. So now we're going to do some more math. We're going to see what happens to this system after this collision happens. So now it says calculate the momentum of the system after the gliders collide with each other. So same thing as we did before. The momentum of the system is going to be the momentum of the one plus the momentum of the other. So glider 1, I have P equals mv. The mass is still 2. The velocity we looked at, right? The velocity is 2.5 now. Why did it slow down? And this gives me a total momentum of 5 kilogram meters per second. Glider 2, P equals mv. The mass is still 2. The velocity is also 2.5. This gives me a momentum for glider 2 of 5 kilogram meters per second. All right, so the momentum of the system is the momentum of glider 1 plus the momentum of glider 2. So I have 5 plus 5. So my system still has a momentum of 10 kilogram meters per second. Even though each glider is different, the momentum of the system is the same. And this also explains why the velocity changed, right? So when those 2 gliders hit each other, glider 1 slowed down, so the velocity went down. Glider 2 started to move, so the velocity went up, right? So their masses didn't change, but just like we did last time, we noticed that their velocities changed because there's that impulse that happens, right? Glider 1 hits glider 2, there's some force there. The force changes the momentum of each of those gliders, but the system, the total of both of them, stay the same. All right, so let's do some comparing. What do we notice about the momentum of each glider before and after the collision? So glider 1, before the collision was 10 kilogram meters per second, and after the collision was, after the collision was 5 kilogram meters per second. Glider 2, before the collision was 0 kilogram meters per second, and after the collision was 5 kilogram meters per second. Okay, so it's your turn again. How does the momentum of each glider change after the collision? So pause, write down your observation. How does the momentum change after the collision? Okay, so now let's look at the system, right? Here's the system again. So before the collision, the momentum of this system was 10 kilogram meters per second. After the collision, the momentum is still 10 kilogram meters per second. So now it's your turn again. How does the momentum change? Ooh, trick question, right? After the collision. So how does the momentum of the system change after the collision? Pause the video, write down your observation, and then we'll finish. Okay, last thing then. How does Newton's law work in all of this? Right? How does Newton's law work in all of this? So remember up at the top, we said that Newton's law, Newton's third law, is all about equal and opposite forces. So what we're going to say here is that since the force, and that's another way to talk about impulse, right, is equal for both gliders, right? So when glider 1 hit glider 2, that force is the same as glider 2 pushing back on glider 1. So those forces are equal and opposite. So since the force or the impulse is equal on both gliders, that means the change in momentum, right, so I abbreviated a little bit, is equal for both gliders. It's just opposite. The momentum for glider 1 went down. The momentum for glider 2 went up. So the system was constant. All right. As always, if you have any questions, make sure you write them down in here so we can talk about them next class. And that's all for today. So thank you very much. Oh, I almost forgot. So can you now talk about the conditions, equal and opposite? I'm sorry, not equal and opposite. Closed and isolated, you know what those things are. How does Newton's third law relate with impulse? And how do we use, oh, we didn't talk about predicting the behavior, did we? Okay, well, I'll put that on the next one. Thank you very much. I'll see you in class.